Welcome back. Today, let us see how to design a floating point encoder. Floating point encoder. The purpose of this system is to convert the fixed point number into floating point. So that what is the advantage is, by using floating point notation, the number of bits can be reduced. So when the number of bits can be reduced, the memory requirement is also reduced. That is the advantage. Okay. So in this example, we are converting 11-bit fixed point notation into 7-bit floating point notation. Okay. Now in the floating point notation, the number is represented in the form of m into 2 power e, where m represents mantissa consisting 4 bits, whereas e is the exponent consisting 3 bits. So totally 7 bits. Okay. So this is a notation for floating point number. Okay. 11 bit number is converted into 7 bits. For example, if you take this number as an example, okay. So here, how in the floating point notation, from the MSC question, you need to check out where the logical one appears. From that question, 4 bits are considered as the mantissa. Okay, so here the MSB 4 bits 1101 is the mantissa. Okay, the rest of the bits count. How many bits are the rest? 1, 2, 3, 4, 5, 6, 7. So 7 bits. So exponent is 7. So 1101 into 2 power 7. So this is the floating point number, whereas this is the fixed point number. In the fixed point notation, it is 11 bits, whereas in the floating point notation, it is just totally 7 bits. Okay, 4 for mantissa, 3 for exponent. Okay, but in the floating point notation, the number is not exactly equal to fixed point notation. There is a slight error in between them, but it is very less, hence negligible. Okay. Similarly, if you take the second example, by observing from the MSU question, in the third location we have 1. Okay. So from that point, 4 digits are treated as a mantissa. The rest of the bits is the exponent. So mantissa is 1001 and the rest of the bits are 5. Therefore, exponent is 5. Okay. Coming to third example. So from this question, the one starts. From this, 4 bits are considered as the mantissa. The rest of the bits are only 2. So therefore 2 power 2. So like that you can convert the fixed point number into floating point notation. Okay. Now this is the diagram to convert the fixed point number into floating point number. So to design such a system, you need to use one priority encoder 74148 priority encoder 8 by 3 priority encoder and 3 multiplexers. These are the 8 by 1 multiplexers. This is one 8 by 1 multiplexer. This is another 8 by 1 multiplexer. This is one more 8 by 1 multiplexers. Okay. So here care has to be taken connecting properly the 11-bit data as an input to the priority encoder and multiplexers. Okay. So with reference to priority encoder, from the MSV question to 8 bits you need to apply to the priority encoder, that is B10 to B3. Okay, suppose B is the input number, so B10 position to B3 position value has to be applied as an input to the priority encoder. Then from B9 to B9 to B9 to B2, B9 to B2 8 bits are applied as an input for the first multiplexer. Then B9 8 to B1 are the 8 bits are applied to the second multiplexer. B7 to B0 are the input bits for the third multiplexer. Okay. So now based on this data, okay. So you know from where the exponent position is. The output of the encoder decides the exponent value. The group select output of the exponent is the M3 bit, whereas M2, M1, M0 are the multplexer outputs. Okay. So with reference to our data, what is our data? Which one I have taken? Second one I have taken as an input. Okay. So therefore the mantissa is 1001 into 2 power 5 you need to get. Okay. So but here the output is in the active low notation. That's why instead of 1001 we are getting 0110. In place of mantissa, 5 means in active high case 101, whereas in active low means 010. Okay, so like that it converts the fixed point notation into the floating point notation. To take some more examples and practice on this diagram. Okay. Then coming to coming to that dual priority encoder. See another system dual priority encoder. Okay. So what is the purpose of dual priority encoder is, so you know the 74148 priority encoder represents first priority input. Okay. Whereas this dual priority encoder represents, it also gives, in addition to first priority input, also gives second priority encoder. I mean second priority input. It also shows second priority input. Okay. So now whatever the data in which you need to know the priorities, first of all apply that data to the 174148, so that it gives to which the first priority has to give. So with reference to this, I5 is the first priority. Assume this is the original data. With reference to this data, first priority to 5, second priority to 2. Second priority input is 2. So the output of the first encoder gives 5 value, whereas the second priority output you can get from this priority encoder. This is also 74148. It shows the 2, but in active low. Okay, active low model it represents. Okay, so for that, so this is the input for the first priority encoder, so that the output is 5. So while giving the data to the second priority encoder, you need to make the fifth bit position 1. Then only the second priority encoder shows its priority input is 2. Okay, so to make it 0, we are going to use the additional network, that is 3 to 8 decoder and some this NAND gate circuit. Here how their operation I represented clearly, so that the first one gives value of 5, the second priority encoder gives the value of 2. Okay, that is the way you can see the priority encoder is a dual priority encoder, right? So you check out with some more examples. So if you have any doubts, you just take the clarification.